Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the Oort Cloud, exploring the frozen edge of our solar system. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The Oort Cloud, a hypothetical collection of icy bodies, represents the outermost boundary of our solar system, existing at a distance of approximately 50,000 to 100,000 astronomical units from the Sun. This enigmatic region was first proposed by the Dutch astronomer Jan Oort in 1950. Building upon earlier theories of cometary origins, it serves as a reservoir for long-period comets, with these celestial objects occasionally being nudged inward by gravitational interaction. Historically, this region has been shrouded in mystery as its existence remains unobserved directly. The assumption of its presence arises from the behavior of comets that travel from the distant reaches of the solar system toward the inner planets. Observations indicate an influx of these icy wanderers, suggesting a source beyond the known planets. This proposed cloud, composed mainly of water, ammonia, and methane ice, is believed to contain trillions of individual icy objects, some with diameters exceeding 100 kilometers. The Oort Cloud's formation is theorized to have resulted from the gravitational influence of the early solar system, with leftover materials from the process of planetary formation being pushed to the fringes. Such insights provide a glimpse into not only the structure of our solar system, but also the dynamic processes that govern its evolution across billions of years. Defining the Oort Cloud reveals a vast spherical shell enveloping the solar system, extending from approximately 2,000 to 100,000 astronomical units from the Sun. This region comprises countless icy bodies, remnants from the solar system's formation, composed primarily of water ice, carbon dioxide, ammonia, and other volatile compounds. These objects remain in a state of relative stasis due to the immense distances involved. The Oort Cloud is generally divided into two distinct zones, the inner and outer Oort Cloud. The inner region contains a denser concentration of objects, while the outer stretches into the cosmic void, becoming increasingly sparse. This arrangement creates a gradient of composition and density, with the inner region often exhibiting a higher incidence of cometary activity as gravitational interactions draw some bodies inward toward the Sun. These icy bodies, while small in size, contribute significantly to our understanding of the early solar system. They serve as time capsules, preserving primordial material and providing insights into the conditions of the early solar nebula. Each fragment bears witness to the complex processes that shaped planetary formation, the accretion of materials, and the eventual development of the planets themselves. Through continued observation, this region holds the potential to unravel further mysteries of our cosmic origins. The formation of the Oort Cloud is a subject of intriguing theories and mechanisms. As the solar system evolved from a primordial disk of gas and dust, icy bodies began to coalesce in the outer reaches. Gravitational interactions with the gas giants played a crucial role, flinging these icy objects outward into the vastness of space. Over millions of years, a spherical shell of these remnants formed, creating a vast reservoir of potential comets and other celestial bodies. This region, situated far beyond the orbit of Neptune, is thought to encompass a vast area, extending roughly 100,000 astronomical units from the Sun. The distance from the inner solar system gives rise to a cold environment, where temperatures plummet to near absolute zero. Within this frigid expanse, countless icy bodies, composed mainly of water, ammonia, and methane, reside in a state of suspended animation. Models suggest that perturbations such as the gravitational influence of passing stars or the Milky Way's tidal forces can occasionally disturb these objects, sending them hurtling towards the inner solar system. This process initiates the transformation of dormant icy bodies into magnificent comets, which, as they approach the Sun, reveal their beautiful tails. Understanding the formation of this distant region offers profound insights into the early solar system and the processes that shaped its evolution. The differentiation of the Oort Cloud reveals two distinct regions, each characterized by unique properties and formations. The inner Oort Cloud, often termed the Hills Cloud, exhibits a relatively denser structure. Here, icy bodies are more tightly clustered, influenced by the gravitational pull of nearby giants and the solar wind. Comets originating from this area tend to have shorter orbital periods, completing their journeys around the Sun in mere years or decades. In contrast, the outer Oort Cloud, or the spherical shell that envelops the inner region, is sparsely populated. This expanse extends far beyond the gravitational influence of the Sun, resulting in an environment where objects drift freely in vast distances. Comets originating from this section possess long orbital periods, taking thousands or even millions of years to complete a single revolution. The dynamics of these icy bodies are influenced by passing stars and the gravitational interactions that can perturb their orbits. The temperature in these distant reaches approaches near absolute zero, allowing volatile compounds to remain frozen. This characteristic grants the outer Oort Cloud its unique identity, acting as a reservoir for primordial materials. These remnants, untouched for eons, hold critical information about the conditions that prevailed during the formative years of the solar system. Understanding these regions contributes to a broader comprehension of celestial mechanics and the life cycles of comets. Characteristics of the Oort Cloud reveal a diverse array of icy bodies, remnants from the early solar system. These objects, primarily composed of water ice, carbon dioxide, ammonia, and other volatile compounds, exhibit varied sizes, ranging from microscopic grains to colossal nuclei measuring tens of kilometers across. The vast distances separating them contribute to a sparse distribution, creating a vast, nearly empty region surrounding the solar system. Comets, as the most recognizable inhabitants of the Oort Cloud, possess elliptical orbits that can extend far into interstellar space. When these icy bodies approach the Sun, they undergo sublimation, releasing gas and dust that form their distinctive tails. This process highlights their dynamic nature, contrasting sharply with their otherwise dormant existence in the frigid depths of the cloud. Beyond comets, other objects in this region include potential dwarf planets and smaller icy bodies, which may serve as critical clues to understanding the solar system's formation and evolution. The interaction of these bodies with the gravitational influence of nearby stars can occasionally send them on trajectories toward the inner solar system, leading to observable phenomena. The study of these frozen relics enhances knowledge of the early solar system environment, providing insight into the conditions that prevailed during its formation and the subsequent development of planetary bodies. Gravity plays a crucial role in maintaining the structure of the Oort Cloud. This vast region, extending from about 2,000 to 100,000 astronomical units from the Sun, relies on gravitational forces to keep its icy objects bound within its expansive boundaries. The mass of the Sun, combined with the influence of other celestial bodies, creates a delicate balance that shapes this distant cloud. Within this spherical shell, gravitational interactions dictate the orbits of countless comets and planetesimals. The gravitational pull from the Sun is strong enough to retain these bodies, yet not so overwhelming as to disrupt their overall arrangement. This equilibrium allows for a diverse range of orbits, some highly elliptical, reflecting the varying conditions under which they formed. As objects enter the inner solar system, gravitational nudges from the giant planets, particularly Jupiter and Saturn, can alter their paths, influencing their eventual fates. Such interactions are vital for understanding the dynamics of the Oort cloud and its long-term stability. The delicate interplay of these gravitational forces reveals much about the underlying structure of our solar system. It highlights the significant role of gravity, not only in shaping the Oort cloud, but also in the broader context of cosmic evolution, emphasizing the intricate connections between distant regions and the central star that anchors them. The gravitational influence of nearby stars extends far beyond their immediate vicinity, subtly affecting the dynamics of the Oort cloud. This region, composed of icy bodies and debris, is delicately balanced by the gravity of celestial neighbors. The passage of a star through the solar neighborhood can impart gravitational perturbations that alter the orbits of these distant objects, occasionally sending them into the inner solar system. When a star approaches, its gravitational field interacts with the Oort cloud, inducing changes that can lead to the ejection of certain icy bodies. These interactions occur over vast timescales, shaping the population and distribution of the cloud's constituents. As a result, this region is not a static entity, but rather a dynamic environment, constantly reshaped by external forces. The periodic influx of comets into the inner solar system is a direct consequence of these gravitational interactions. As icy bodies are nudged from their tranquil orbits, they embark on long journeys toward the Sun. The arrival of these comets provides invaluable insights into the primordial materials from which the solar system formed, revealing the conditions of the early solar nebula. Understanding the influence of nearby stars offers a glimpse into the intricate gravitational dance that governs the cosmos. It underscores the importance of studying the Oort cloud as a window into the processes that shape our solar neighborhood and beyond. The immense distance of the Oort cloud presents significant challenges in measurement. Situated approximately 50,000 astronomical units from the Sun, its vast expanse stretches across the outer limits of the solar system. It is enveloped in a near-total darkness, making direct observation nearly impossible. The faint light from its icy bodies barely penetrates the void, complicating efforts to quantify their size and distribution. Indirect methods become crucial for understanding this distant region. Observations of long-period comets provide vital clues. These celestial objects, believed to originate from the Oort cloud, offer insights into its composition and structure. Tracking their orbits helps infer the gravitational influence exerted by the solar system's outer reaches. The interactions between these comets and the gravitational pull of nearby stars also reveal the dynamic nature of this remote shell. Models of the Oort cloud suggest it may contain billions of icy bodies, with some estimates indicating a population in the range of 1 trillion. Each fragment holds a record of the early solar system, preserved in the frigid temperatures of this outer realm. The challenge remains in isolating these objects from the surrounding cosmic noise as they drift silently in the cold dark, awaiting the moment when they may reveal their secrets through the occasional visit to the inner solar system. Defining the limits of this region, the Oort cloud extends far beyond the orbits of the planets, with estimates suggesting it lies between 2,000 and 100,000 astronomical units from the Sun. The outer boundary appears to merge with the interstellar medium, creating a gradual transition that blurs the lines of solar influence. Objects within this vast area are thought to be remnants from the early solar system, icy bodies formed in the cold, distant reaches of space. This boundary is not sharply defined. It reflects a gradient of gravitational influence where the Sun's pull wanes, allowing interstellar forces to exert their own influence. Comets originating from this region often exhibit elongated orbits, suggesting interactions with passing stars may disturb their paths, nudging them into the inner solar system. The vast distances involved present significant observational challenges. The faint and distant nature of these icy bodies means they are often overlooked, lost in the expanse of space. Efforts to survey the Oort Cloud rely on powerful telescopes and computational models designed to predict their positions and movements. The understanding of this boundary shapes our comprehension of the solar system's formation and evolution, illustrating the intricate balance between gravitational forces and the ancient remnants that linger at its fringes. Theoretical models suggest that the Oort Cloud originated from the debris of the early solar system. This vast reservoir of icy bodies is believed to have formed through a combination of processes, including gravitational perturbations from nearby stars and the influence of the gas giants. These interactions likely scattered materials outward, resulting in a vast spherical shell encircling the solar system. Some hypotheses indicate that the cloud may have originated as a protoplanetary disk, where icy particles coalesced over time. As the solar nebula evolved, gravitational interactions with larger bodies caused these particles to be ejected, forming the distant reservoir observed today. This scenario highlights the dynamic nature of celestial mechanics, where even the smallest forces can lead to significant outcomes over astronomical timescales. The distinction between the inner and outer regions of the Oort Cloud is another key aspect of its origin. Those closest to the solar system may have been influenced primarily by the gravitational pull of the giant planets, while those further out were shaped by interactions with passing stars and the interstellar medium. Such processes underscore the delicate balance maintaining this distant shell of icy remnants. Understanding the formation of the Oort Cloud not only provides insights into the solar system's history, but also offers a glimpse into the evolution of planetary systems throughout the cosmos. The discovery of the Oort Cloud is rooted in the early 20th century, when astronomers began to piece together the complexities of the solar system. Theoretical foundations were laid by Jan Oort, who proposed the existence of this distant cloud in 1950. His hypothesis emerged from observations of long-period comets, which exhibited trajectories that suggested a reservoir far beyond the known planets. This realization indicated that such celestial bodies could originate from a vast spherical region encircling the solar system. During the decades that followed, the notion of the Oort Cloud gained traction. It became increasingly clear that these icy bodies, which can travel vast distances, represent remnants from the formation of the solar system. An understanding emerged that its existence could explain the unpredictable arrivals of comets, which seemed to defy the gravitational influences of nearby planets. The absence of direct observation, however, presents a challenge, as distances involved render detection nearly impossible with current technology. Theoretical models emerged, detailing the cloud's structure and composition, suggesting it extends from approximately 2,000 to 100,000 astronomical units from the Sun. This vast region, with its icy bodies and potential for new discoveries, continues to spark intrigue among scientists, framing ongoing research into the origins and dynamics of our celestial neighborhood. Long-period comets emerge from the Oort Cloud, a distant reservoir of icy remnants from the solar system's formation. These celestial wanderers take orbits that can last thousands, even millions of years, tracing elongated paths that span vast distances. When a comet is disturbed, possibly by the gravitational influence of nearby stars, it begins its journey toward the inner solar system. The journey transforms these icy bodies, which predominantly consist of water ice, carbon dioxide, ammonia, and other volatiles. As they approach the sun, they experience significant heating, causing sublimation of ice into gas. This process creates a glowing coma and often a pronounced tail, which can extend millions of kilometers into space. The interaction with solar radiation and the solar wind defines their appearance, often resulting in striking visual displays. Long-period comets can originate from various parts of the Oort Cloud. The cloud is thought to be spherical, stretching from approximately 2,000 to 100,000 astronomical units from the Sun. This vast distance means that only a few comets may be observed at any given time, leading to periods of relative inactivity interspersed with bursts of frequent sightings. Understanding their origins and trajectories provides valuable insights into the early solar system and the processes that shaped its evolution. The Oort Cloud exists in a delicate balance with the Kuiper Belt, each region contributing distinct characteristics to the solar system's structure. Positions beyond the orbit of Neptune, the Kuiper Belt consists of icy bodies, including dwarf planets such as Pluto. This region serves as a repository for short-period comets, which have relatively brief orbits around the Sun. In contrast, the Oort Cloud, situated at a greater distance, is thought to harbor long-period comets. These icy bodies are influenced by gravitational interactions with nearby stars and the galactic tide, resulting in their ejection into orbits that can take thousands to millions of years to complete. The relationship between these two distant realms highlights the dynamic processes at play in the solar system. Interactions between objects in the Kuiper Belt can occasionally send comets into the inner solar system, while perturbations in the Oort Cloud can lead to the emergence of comets from its vast expanse. The gravitational influence of nearby celestial bodies, star passages, and galactic forces orchestrate the movements of these icy remnants. Studying the distinctions and connections between the Oort Cloud and Kuiper Belt enhances the understanding of the solar system's formation and evolution, revealing the intricate web of interactions that govern these distant regions. The movement of the Sun through the Milky Way influences the Oort Cloud significantly. As it traverses the galactic spiral arms, it provides a dynamic backdrop against which this distant reservoir of icy bodies exists. The gravitational forces exerted by nearby stars and interstellar gas can perturb the orbits of comets, sending them spiraling inward towards the inner solar system. Such perturbations can lead to a cascade of interactions, forcing these icy remnants to alter their paths and possibly become visible to observers on Earth. The Sun's orbit around the galactic center, completing a journey every 250 million years, affects the stability of the Oort Cloud. Periodic passages through regions of higher stellar density can increase the likelihood of gravitational encounters, contributing to the delivery of new comets into the inner solar system. These encounters are not random. They depend on the Sun's position and movement within the galaxy. Additionally, the influence of the solar wind, a continuous stream of charged particles emitted by the Sun, can also play a role. As it interacts with the Oort Cloud, the solar wind creates a boundary that defines the outer limits of the solar system. It delineates the transition between the solar influence and the vast expanse of interstellar space, marking an essential threshold for these ancient, frozen remnants. Galactic forces exert a profound influence on the Oort Cloud, shaping its structure and dynamics. These remnants exist in a tenuous balance, held together by the gravitational pull of the Sun, yet subject to perturbations from nearby stars and the gravitational waves generated by the Milky Way's spiral arms. As stars traverse the galactic plane, their gravitational fields interact with the cloud, occasionally nudging objects out of their stable orbits. This region is not isolated. It is affected by the tidal forces of the galaxy. The movement of these celestial bodies within the Oort Cloud can lead to the occasional ejection of comets into the inner solar system. These comets, often originating from the far reaches of the cloud, are remnants of the primordial solar nebula, carrying with them clues about the early solar system's formation. Interactions with molecular clouds and dark matter can also influence the cloud's stability. The density of surrounding galactic material can create localized gravitational fluctuations, which may alter the trajectory of individual icy bodies. Over time, these subtle forces contribute to the gradual diffusion of the Oort Cloud, resulting in a slow but constant evolution of its composition and distribution. The delicate interplay of these influences underscores the complexity of this remote region, where ancient relics drift in silence, shaped by the unseen hands of the cosmos. Ices and minerals comprise the building blocks of Oort Cloud objects, revealing a rich chemical diversity. These celestial bodies primarily consist of volatile compounds, including water ice, carbon dioxide, ammonia, and methane. This frozen composition reflects the primordial material that formed the solar system, preserved in the frigid expanse beyond the planets. The low temperatures allow these substances to remain in solid form, forming a thick crust around the rocky cores that may also contain silicate minerals and metals. Various objects within this region exhibit different characteristics based on their formation and evolutionary history. Some are thought to be remnants from the early solar system, while others may have originated from the Kuiper belt, having been ejected into this outer domain by gravitational interactions. The presence of organic molecules suggests that these distant entities could offer insights into the building blocks of life. Spectroscopic studies indicate that many Oort Cloud objects possess a variety of complex hydrocarbons, indicative of chemical processes that occurred in their icy surfaces. Over time, cosmic radiation and solar winds may alter these surfaces, leading to a gradual transformation. This ongoing evolution contributes to the intrigue surrounding these icy bodies, which continue to captivate scientists seeking to understand the origins of our solar system and the potential for life beyond our planet. The gravitational influence of the Sun shapes the delicate orbits of Oort Cloud objects, which are believed to extend from approximately 2,000 to 100,000 astronomical units from the Sun. These distant icy bodies exhibit a range of trajectories, some remaining stable while others are subject to perturbations from nearby stars or galactic tides. The interaction with these external forces can lead to significant alterations in their paths, causing them to spiral inward toward the inner solar system. Ejection mechanisms play a crucial role in the dynamics of this region. The chaotic environment of the Oort Cloud results in the occasional ejection of objects, often triggered by gravitational encounters. When a nearby star passes sufficiently close, it can disrupt the gravitational equilibrium, sending a fraction of these icy bodies into hyperbolic orbits. This process not only contributes to the diversity of long-period comets observed in the inner solar system, but also serves as a reminder of the intricate ballet of forces shaping the solar neighborhood. The study of these ejected objects provides insights into their composition and history. As they travel through the inner solar system, they reveal clues about the primordial materials that formed the solar system, enhancing our understanding of planetary formation and the conditions that may foster life elsewhere in the universe. Planetary encounters play a significant role in shaping the Oort Cloud, influencing its structure and dynamics. As celestial bodies traverse the solar system, their gravitational interactions can perturb the orbits of icy objects within this distant region. These encounters can eject material from the Oort cloud, sending comets into trajectories that bring them closer to the Sun. The gravitational pull of the gas giants, particularly Jupiter and Saturn, significantly contributes to these perturbations. This gravitational influence creates a dynamic environment where objects can gain or lose energy, thereby altering their paths over time. Some may be flung outward into interstellar space, while others may enter the inner solar system, becoming visible as bright comets. The distribution of objects within the Oort cloud is not uniform. It is shaped by these encounters, resulting in a complex structure populated with a diverse range of icy bodies. Observations of cometary activity provide valuable insights into the processes at play. Each comet, as it approaches the Sun, unveils fragments of the primordial material that has remained largely unchanged since the solar system's formation. Through these interactions, the Oort cloud serves as a reservoir of ancient building blocks, preserving the history of our solar system's evolution and offering a glimpse into the mechanisms that could influence other planetary systems across the galaxy. Current missions aimed at exploring the Oort cloud focus on expanding our understanding of this distant region. The theoretical models suggest that a dedicated spacecraft could provide unprecedented insights into its composition and structure. Instruments capable of detecting faint signals from icy bodies would illuminate the nature of these primordial remnants, revealing their physical and chemical properties. Future missions may utilize advanced propulsion systems to traverse the vast distances involved, enabling a deeper examination of the cloud's innermost regions. Such endeavors would likely involve flybys of scattered objects, potentially including long-period comets that originate from this area. These encounters could yield crucial data regarding the formation processes of the solar system. In addition, collaborative international efforts are underway to enhance observation capabilities. Ground-based telescopes and space observatories continuously monitor the sky, seeking to identify new comets and other trans-Neptunian objects that may originate from the Oort cloud. This ongoing surveillance helps refine models of the cloud's structure and dynamics. As missions evolve, the integration of artificial intelligence and machine learning will play a pivotal role in analyzing vast datasets. These technologies can identify patterns and predict the behavior of these distant objects, facilitating a more profound understanding of their origins. Each discovery will incrementally build the knowledge necessary to interpret the role of the Oort cloud within the broader context of cosmic evolution. Observing the Oort cloud presents significant challenges due to its vast distance from the Sun and the faintness of its components. Located at the outermost reaches of the solar system, it lies approximately 50,000 to 100,000 astronomical units away. This immense separation renders direct imaging practically impossible, necessitating innovative techniques to gather data. Telescopes equipped with advanced technology enable astronomers to detect the faint scatter of light from objects within this region. Ground-based observatories, often enhanced with adaptive optics, mitigate atmospheric distortions, providing clearer views of the night sky. Space telescopes, positioned beyond Earth's atmosphere, offer an unobstructed perspective, facilitating the observation of distant icy bodies. Computer models play a crucial role in these efforts. By simulating the dynamics of the Oort cloud, researchers can predict where potential comets may emerge. These models rely on gravitational interactions, which dictate the orbits of celestial objects, allowing scientists to estimate the population and distribution of bodies within this icy reservoir. As insights accumulate, understanding the Oort cloud's composition becomes increasingly feasible. Observations of long-period comets believed to originate from these frigid regions contribute valuable clues about the primordial materials that formed the solar system. Each finding enhances the comprehension of these distant remnants and their significance in the cosmic narrative of our existence. Research into this region of icy bodies extends its relevance beyond mere celestial mechanics. The Oort Cloud, viewed as a reservoir of primordial material, offers clues about the formation and evolution of the solar system. Studies within this distant boundary contribute to understanding the origins of water and organic compounds, crucial ingredients for life as it is known. Unraveling the mysteries of these ancient relics allows scientists to investigate the conditions that may have catalyzed life's emergence on Earth. The materials found in this region may have been delivered to our planet through cometary impacts, thereby influencing chemical processes essential for life. These investigations also inform the search for extraterrestrial life beyond our solar system. By studying the composition and behavior of Oort Cloud objects, researchers gain insights into planetary formation in other star systems. This enhances the understanding of potential habitable zones and the types of materials that can foster life elsewhere in the universe. In addition, the dynamics of comets originating from this region provide a framework for predicting similar phenomena in other star systems. Such knowledge is invaluable in the context of astrobiology, as it helps to delineate the pathways that life-supporting elements may take across cosmic distances. The implications for our understanding of life's universality continue to expand as research progresses. The collisional history of the Oort Cloud reveals a dynamic, albeit distant environment shaped by impacts and fragmentation. Composed primarily of icy bodies, this region is influenced by gravitational interactions and the remnants of past collisions. The faint glow of comets, originating from these distant reaches, serves as a reminder of the ongoing processes at play. Objects within the Oort Cloud experience occasional encounters, leading to fragmentation as larger bodies break apart. This phenomenon generates a cascade of smaller particles, contributing to the cloud's complexity. Each collision possesses the potential to alter trajectories, sending some objects inward toward the inner solar system. The subsequent journey can eventually lead to their discovery as they become visible from Earth. These interactions are not solely destructive. They also facilitate the formation of new entities as fragments amalgamate under the influence of gravity. The ongoing cycle of creation and destruction underscores the importance of studying this region. By understanding the collisional dynamics, insights into the solar system's evolution can be garnered. The faint whispers of the Oort Cloud reveal a rich history, one that shapes not only the distant icy bodies, but the broader solar system itself. Each collision and fragment adds to the narrative of existence, hinting at the complexities woven within the icy veil at the edge of our cosmic neighborhood. The quest for new objects within this distant region remains a pivotal endeavor in modern astronomy. Continuous advancements in observational technology allow astronomers to penetrate the icy depths and unveil celestial bodies previously obscured from view. The utilization of powerful telescopes equipped with advanced imaging techniques enhances the ability to detect the faintest glimmers of light emanating from these frigid relics. Identifying new objects within the Oort Cloud poses significant challenges. The vast distances involved mean that even the most luminous objects appear dim. Many of these icy bodies exhibit highly elliptical orbits, often taking thousands of years to complete a single revolution around the Sun. This orbital behavior necessitates prolonged observation periods, as fleeting encounters with these objects can lead to their disappearance from view. Computer models and simulations play a crucial role in predicting the locations of potentially undiscovered objects. They help scientists estimate the distribution and mass of these icy bodies, guiding targeted observations. Efforts have intensified, particularly with the advent of survey projects designed to systematically map the sky. These initiatives aim to catalog the existing population, while seeking out new celestial entities hidden within the Oort Cloud's icy embrace. Each discovery enriches the understanding of the solar system's formation and evolution, revealing the intricate dynamics that govern this remote realm. The Oort Cloud's vast expanse presents a unique opportunity for interstellar travel, potentially serving as a gateway to the cosmos beyond. Its location, lying at the fringes of the solar system, offers a vantage point from which to launch missions into the interstellar medium. The dense concentration of icy bodies, along with their varied compositions, could provide resources essential for long-duration spaceflight. Navigating through this region may enable the development of new propulsion technologies. Utilizing materials found within the Oort Cloud, spacecraft could be equipped with advanced systems designed for deep space exploration. The low gravitational influence of these distant objects allows for more efficient maneuvers, reducing the energy required to reach significant velocities. Research indicates that the dynamics of the Oort Cloud might also yield insights into the behavior of comets and the potential for using them as navigation markers. The transient nature of these icy bodies, influenced by passing stars, could pave the way for understanding gravitational assists that propel spacecraft on their journeys. The prospect of harnessing the Oort Cloud as a stepping stone encourages a re-evaluation of humanity's capabilities in traversing the universe. Each theoretical journey into the unknown challenges existing paradigms, fostering a deeper appreciation for the intricate architecture of the cosmos and the potential that lies beyond. The ice giants exert a significant gravitational influence on the Oort Cloud, a distant ring of icy bodies surrounding the solar system. Their immense mass shapes the dynamics of this remote region, where comets and other small celestial objects reside in a state of suspended animation. The gravitational pull from these giants can perturb the orbits of particles within the cloud, occasionally sending them hurtling towards the inner solar system. This interaction leads to a delicate balance, as the ice giants maintain the cloud's stability, while also facilitating a stream of comets that may eventually become visible from Earth. The influence of these distant titans extends beyond mere gravitational interactions. They play a crucial role in the cycling of material throughout the solar system. As comets are nudged into the inner regions, they can contribute to the delivery of water and organic compounds to terrestrial planets, potentially fostering the conditions for life. Observations suggest that the ice giants, with their unique compositions and orbital patterns, may hold keys to understanding the history and evolution of the Oort Cloud. Their presence raises essential questions about the formation of this icy reservoir and the mechanisms that govern its behavior. Ongoing research aims to unravel these complexities, deepening the understanding of our solar neighborhood's vast and largely unexplored outskirts. The Oort Cloud serves as an essential window into the early solar system. This distant spherical shell of icy bodies is thought to harbor remnants from the formative years of planetary development. Composed mainly of frozen gases and volatile substances, these objects offer insight into the primordial materials that coalesced to form the planets. Their preservation in the frigid depths of space provides a unique opportunity to study the conditions that existed approximately 4.5 billion years ago. As comets from the Oort Cloud make their occasional journeys into the inner solar system, they carry with them clues about the chemical and physical processes that shaped the early environment. The isotopic compositions of these icy visitors can reveal information about the molecular building blocks that contributed to the emergence of life on Earth. And such analyses can illuminate the complexities of chemical evolution, hinting at how organic molecules may have formed. In addition, the gravitational dynamics of the Oort Cloud contribute to the broader understanding of the solar system's evolution. Interactions with nearby stars may occasionally disturb the delicate balance of this region, sending a few bodies into trajectories that may eventually lead them toward the inner solar system. Understanding these dynamics requires sophisticated modeling techniques. Scientists employ various simulations to recreate the gravitational influences exerted by passing stars and the Sun itself. These models incorporate the complex gravitational interactions and the vast distances involved, painting a clearer picture of the Oort cloud's behavior over time. Each simulation provides insight into how the cloud's icy bodies respond to perturbations. They reveal potential pathways of comets, offering predictions about which objects might become visible from Earth. By examining the statistical outcomes of countless scenarios, researchers can ascertain the likelihood of specific comets entering the inner solar system. This predictive capacity is crucial for both scientific inquiry and practical observation. Oort Cloud remains largely unobserved, making these models vital for understanding its structure and dynamics. They not only inform astronomers about the cloud's population, but also help identify the origins of long-period comets. Such insights enhance our comprehension of the early solar system and its formation processes. The interplay between theoretical models and observational data solidifies the understanding of this distant region. As technology advances, simulations will continue to refine the knowledge surrounding these icy relics, illuminating the enigmatic boundaries of our solar environment. Seasonal variations in activity within the Oort cloud reveal intriguing patterns that reflect the delicate balance of gravitational influences and solar radiation. As the Earth orbits the Sun, the gravitational effects from nearby stars can perturb the orbits of some of the icy bodies, nudging them towards the inner solar system. This phenomenon is most pronounced during specific times of the year, leading to a periodic increase in the visibility of comets originating from this distant region. The intensity of solar radiation fluctuates throughout the seasons, affecting the sublimation rates of volatile materials found on the surfaces of these icy bodies. During the warmer periods, the increase in solar energy can cause temporary outgassing, producing tails that become visible as these objects approach the inner solar system. This seasonal activity serves as a reminder of the dynamic processes occurring even in the most remote reaches of our celestial neighborhood. Observations of these seasonal cycles contribute to our understanding of the Oort cloud's structure and composition. Variations in brightness and trajectory provide clues to the distribution of its constituents, while the timing of increased cometary activity offers insights into the complex gravitational interactions at play. These findings enhance our comprehension of the solar system's evolution and the mechanisms that govern the life cycles of its most distant inhabitants. The presence of cosmic rays in this region contributes significantly to the complex interactions taking place in the Oort cloud. These high-energy particles, originating from supernovae and other astrophysical phenomena, permeate the vast expanse, influencing the chemical composition of icy bodies. When they collide with the primordial materials found in this remote environment, they can initiate a series of reactions that alter the molecular structures of these ancient objects. The interaction between cosmic rays and the icy constituents also generates secondary particles, which further complicate the environment. This radiation plays a crucial role in shaping the surface properties of the comets and other celestial bodies that reside within the Oort cloud. The bombardment induces alterations in the ices, leading to the potential release of gases and other materials that may affect their trajectories as they journey toward the inner solar system. Observations suggest that the cumulative effects of cosmic rays could be instrumental in triggering the fragmentation of larger bodies, resulting in the birth of new comets. These processes contribute to the dynamic nature of the Oort cloud, where ancient relics from the early solar system coexist with the continuous influences of galactic phenomena. Understanding these interactions aids in piecing together the intricate history of our solar system and the evolution of its outermost reaches. Theories surrounding Oort cloud disruption, suggest that gravitational influences from nearby stars or galactic forces can instigate significant changes within this distant region. These perturbations may cause comets to be nudged from their primordial orbits, leading them to embark on paths towards the inner solar system. Such interactions reveal the delicate balance maintained within this icy shell, where the gravitational pull of the Sun interacts with the mass of countless icy bodies. Further examination indicates that these disruptions might not be anomalies, but rather part of a larger cycle of reformation. Over time, as nearby stars pass through the solar neighborhood, they create gravitational waves that ripple through the Oort cloud. The gravitational perturbations can lead to the ejection of certain objects into interstellar space, while simultaneously allowing others to coalesce, forming new cometary bodies. The reformation process establishes a dynamic equilibrium, where the remnants of the original cloud interact with fresh material from the surrounding region. This ongoing cycle contributes not only to the replenishment of the inner solar system's cometary population, but also to the potential for new discoveries regarding the building blocks of planets and the origins of water and organic compounds. Such investigations into the Oort cloud deepen the understanding of its role as a reservoir of ancient material, providing insights into the conditions that prevailed during the early formation of the solar system. The interplay between the Oort cloud and solar wind illustrates a complex dynamic that shapes the outermost regions of the solar system. Solar wind, a continuous stream of charged particles emitted by the Sun, interacts with the icy bodies located within this vast, distant shell. As these particles traverse the vacuum of space, they exert pressure on the tenuous material present in the Oort cloud, influencing the trajectories and behaviors of its constituents. This interaction has implications for the stability of orbits within the cloud, leading to occasional perturbations that can send comets on long, elliptical journeys toward the inner solar system. The delicate balance of forces at play is critical. While solar wind helps to maintain the structure of the cloud, it also introduces a degree of chaos. The interaction with solar radiation results in gradual changes to the surface compositions of these icy objects, revealing the transformation of volatiles into gases. The Oort cloud serves as a boundary, not just physically, but also as a transition zone for the effects of solar activity. Variations in solar wind strength can influence the distribution of material within this region, offering a glimpse into the solar system's evolutionary history. Observations continue to refine the understanding of this interaction, highlighting the Oort cloud's significance in the broader context of cosmic processes. The presence of dark matter plays an essential role in the dynamics surrounding the Oort cloud. This vast region, composed of icy bodies and potential comets, exists at the outskirts of the solar system, influenced by gravitational forces emanating from both visible and invisible matter. Dark matter, which constitutes approximately 24% of the universe, exerts a gravitational pull that affects the motion of celestial objects far beyond the realm of direct observation. In this distant region, the gravitational influence of dark matter contributes to the stability of the Oort cloud. The distribution of these icy bodies is not merely a result of the solar wind and radiation from the Sun. The gravitational interactions with dark matter ensure that the Oort cloud retains its structure over astronomical timescales. This stabilization allows for the preservation of numerous objects, some of which may journey inward toward the inner solar system, potentially becoming visible comets. The dark matter halo enveloping galaxies extends into the vicinity of our solar system, creating a complex gravitational landscape. As researchers delve deeper into the properties of dark matter, the implications for the Oort cloud's existence and longevity provide insights into the formation and evolution of not only our solar system, but also others throughout the universe. Understanding these relationships enhances the broader knowledge of cosmic evolution. Theoretical implications of the Oort cloud on planetary formation extend far beyond its icy boundaries. This distant region serves as a reservoir of comets, providing insights into the primordial materials that coalesced to form planets. Comets originating from this vast expanse contain unaltered remnants from the early solar system. Their composition reflects the conditions present during the formation of the gas giants and terrestrial bodies, allowing scientists to infer the processes that shaped planetary evolution. The interactions between the Oort cloud and the inner solar system play a critical role in understanding planetary dynamics. Gravitational influences from nearby stars and the galactic tide can disturb the orbits of these icy bodies, sending them toward the inner solar system. Upon arrival, they may collide with planets, impacting their geophysical and chemical development. Such events can introduce volatiles and organic compounds essential for life, thus highlighting the interconnectedness of celestial mechanics and biological evolution. Research continues to suggest that the Oort cloud may influence the distribution of materials in this region, leading to variations in planetary atmospheres and surface conditions. These findings underscore the importance of studying this enigmatic zone. Each cometary visit offers a glimpse into the ancient solar system, enriching the narrative of planetary formation and the evolution of celestial bodies. Historical records reveal that comets have long captivated human imagination. Their appearances were often interpreted as omens or messages from the divine, leading to a rich tapestry of folklore and mythology across cultures. The significance of these icy visitors transcends mere superstition. They have served as markers of time, influencing calendars and guiding navigators over millennia. Evidence of their impact is etched in ancient texts, where sightings are meticulously documented. Each comet, with its distinctive tail and varying brightness, sparked curiosity, prompting early astronomers to study their trajectories. Their unpredictable nature inspired advancements in observational techniques, laying the foundation for modern astronomy. Scientific inquiry into these celestial objects reveals much about the conditions of the early solar system. Comets from the Oort cloud are time capsules, preserving primordial materials and volatile compounds that date back to its formation. Analysis of their composition unveils insights into the building blocks of planets and the processes that shaped them. The study of comets continues to fuel exploration, with missions such as the European Space Agency's Rosetta providing unprecedented access to the secrets held within these ancient bodies. The historical significance of comets underscores their dual role as both harbingers of change in human history and as key players in the ongoing story of planetary evolution within the solar system. The Oort cloud stands as a vast spherical shell surrounding the solar system, a reservoir of icy bodies that stretches from approximately 2,000 to 100,000 astronomical units from the Sun. This region serves as a boundary between the known solar system and the interstellar medium, holding potential clues about the origins of comets and, consequently, the building blocks of life. The sheer distance and the sparse density of matter complicate direct observation, yet the presence of these primordial objects hints at the solar system's formative years. In contemplating the Fermi paradox, the quiet vastness of the Oort cloud brings forth questions about the existence of extraterrestrial civilizations. The paradox posits that given the vast number of stars in the galaxy, the lack of evidence for advanced life forms remains perplexing. The remote location of the Oort cloud might serve as a protective barrier, housing potential life forms in a dormant state, shielded from the cosmic chaos that prevails closer to the Sun. The exploration of this region may reveal not only the origins of our own planetary system, but also the conditions that could support life in its various forms. These icy bodies could harbor organic compounds essential to the development of life, suggesting that many more worlds await discovery beyond the realm of our immediate solar neighborhood. The dynamics of this distant region extend their influence far beyond its icy boundaries. The Oort Cloud plays a subtle yet significant role in shaping Earth's climate history. Occasionally, perturbations from nearby stars or passing molecular clouds disturb the delicate equilibrium of this outer region, sending comets on long elliptical paths toward the inner solar system. These comets, composed of volatile materials and dust, can impact terrestrial climates upon their arrival. When they enter the inner solar vicinity, they become visible as bright streaks against the night sky, captivating observers for millennia. Their collisions with Earth can have profound implications for the planet's climate. For instance, the release of gases and particulates from these impacts may trigger short-term climatic shifts, altering temperatures and atmospheric composition. In some instances, large impacts have been linked to significant extinction events, with dramatic consequences for biodiversity. The geological record bears traces of these cataclysmic encounters, revealing a history of resilience and recovery. Understanding the influence of the Oort Cloud on Earth's climate history enhances insight into the planet's evolution. It underscores the interconnectedness of celestial bodies, suggesting that even the most distant regions of the solar system can resonate with the life and climate of Earth, shaping the very conditions for existence. The future of the Oort Cloud presents a compelling landscape of possibilities. This vast region, composed primarily of icy bodies, is predicted to remain largely unchanged for eons, a remnant of the early solar system. Current projections suggest that it will continue to serve as a reservoir for comets, periodically releasing them into the inner solar system. These icy travelers have the potential to influence planetary atmospheres and impact the geological features of Earth and its neighbors. Future observations may reveal shifts in its structure, driven by gravitational interactions with passing stars or the cumulative effects of galactic tides. Such perturbations could lead to increased cometary activity, altering the dynamics of the inner solar system. The current understanding indicates that the Oort Cloud may contain billions of icy objects, each holding clues to the formative years of our celestial neighborhood. Advanced telescopes and observational technologies are poised to enhance our comprehension of this distant region. Insights gathered could reshape theories of planetary formation and the evolution of celestial bodies. The Oort Cloud remains a silent guardian of the solar system's history, quietly reflecting the origins of life as we know it. Its future, marked by both stability and potential upheaval, continues to invite scientific inquiry and contemplation. The delicate balance of forces within this realm fosters an enduring mystery, bridging the past and the future of celestial exploration. A multitude of factors influences the potential for space missions to this distant frontier. The vast distances involved present significant challenges, with the nearest regions lying trillions of kilometers away from the inner solar system. Current propulsion technology struggles to achieve the necessary speeds for timely exploration, necessitating the development of advanced systems capable of sustaining prolonged journeys. Innovative concepts, such as solar sails and ion propulsion, may offer pathways to traverse these expansive voids. Each mission proposal must consider the intricate dynamics of travel through this icy domain, including the gravitational influences of the Sun and distant celestial bodies. Robotic spacecraft, equipped with sophisticated instruments, would be essential in gathering data from this remote environment, analyzing the composition of comets and other icy bodies that populate the cloud. Potential missions could provide insights into the formation of the solar system and the origins of water and organic materials on Earth. These explorations may reveal how the building blocks of life traversed the cosmos, offering a glimpse into the processes that shaped planetary bodies. Understanding the Oort Cloud's role in the solar system's evolution enhances our knowledge of planetary science, contributing to a broader understanding of the universe's complexity and the potential for life beyond our own world. Technological advancements are crucial for exploring the Oort Cloud, a region that remains enigmatic due to its vast distance from the Sun. Current spacecraft technology is limited in range and speed, requiring innovative designs to develop missions capable of reaching these icy objects. Proposals for advanced propulsion systems, such as ion drives or solar sails, are being considered to enable long-duration missions that could traverse the immense gap, which spans 1,000 to 100,000 astronomical units. Communication technology must also evolve. The vast distances involved mean that signals take significant time to travel, necessitating enhanced relay systems and potentially autonomous spacecraft capable of making decisions without immediate Earth-based input. These improvements would ensure a continuous flow of data as these missions explore the outskirts of our solar system. A continuous solar system. Spectrometers and advanced imaging systems will be needed to study the surface and interior characteristics of these distant objects. This knowledge is fundamental for understanding their origins and the processes that shaped them. Collaborative efforts among international space agencies are fostering the sharing of expertise and resources. This cooperative approach increases the potential for successful missions, paving the way for groundbreaking discoveries in this remote frontier of our solar system. The striking presence of comets has long captured human imagination, leaving a profound imprint on cultural narratives throughout history. These celestial wanderers often served as harbingers of change, their luminous tails illuminating the night sky and stirring a sense of wonder and trepidation. Ancient civilizations interpreted their appearances as omens, influencing decisions of leaders and shaping the course of events. Notable comets, such as Halley's Comet, have sparked curiosity and awe, appearing in historical texts and artwork, embedding themselves in collective memory. Observations of these icy bodies have also propelled advancements in astronomy, inspiring significant scientific inquiry. They prompted early scholars to seek understanding of the cosmos, leading to the establishment of foundational astronomical principles. The predictability of their orbits contrasted with the unpredictability of terrestrial affairs, underscoring the juxtaposition between the celestial and the mundane. In literature, comets frequently symbolize transformation, embodying the duality of destruction and renewal. Their fleeting nature resonates with themes of impermanence, prompting reflection on the human condition. They serve as reminders of the vastness of the universe, urging societies to contemplate their place within it. The cultural legacy of comets extends beyond mere observation, intertwining with mythology, art, and scientific progress, shaping the fabric of human understanding of the cosmos. The Oort Cloud has captured the imagination of science fiction writers, serving as a backdrop for narratives that explore the unknown. It often appears as an enigmatic frontier, a realm populated by icy bodies and the potential for extraterrestrial life. These depictions range from awe-inspiring to fantastical, often blurring the lines between established science and creative interpretation. In many stories, it is portrayed as a bustling highway for interstellar travel, where ships navigate through colossal icebergs resembling comets. This vision, while compelling, diverges from scientific understanding. The Oort Cloud is vast and sparse, its icy constituents scattered across an immense expanse. The distance between these objects is often underestimated in fictional portrayals, leading to misconceptions about density and accessibility. Some narratives suggest that the Oort Cloud harbors ancient civilizations or hidden technologies, which reflect humanity's longing for connection beyond Earth. Yet, these themes overlook the cold, inhospitable nature of this distant region. The reality is one of extreme isolation, where temperatures hover near absolute zero, and the absence of light renders it largely invisible to observation. Such interpretations, while imaginative, serve as a reminder of the gap between scientific fact and speculative fiction. The beauty of the Oort Cloud lies not only in its mysteries, but also in how it challenges our understanding of existence beyond our celestial neighborhood. The role of observatories in mapping the Oort Cloud is pivotal for expanding knowledge of this distant region. Ground-based telescopes, equipped with advanced imaging technologies, continuously scan the night sky, seeking faint signals that originate from these icy bodies. Observatories, both terrestrial and space-based, contribute to a collective effort to identify the elusive comets and other objects believed to dwell within this vast expanse. The faint light emitted by these distant particles poses unique challenges, requiring sophisticated techniques to enhance visibility. Infrared observations play a crucial role, as they can detect the heat signatures of these ancient remnants, offering vital clues to their composition and trajectory. The ongoing analysis of data allows scientists to reconstruct the dynamics of the cloud and its interactions with the solar system. This ongoing research reveals the cloud's potential influence on the trajectory of comets entering the inner solar system. Each documented observation enhances understanding of gravitational interactions, particularly with nearby stars. These insights deepen the comprehension of how the Oort Cloud was formed and its evolution over billions of years. In this quiet pursuit of knowledge, the efforts of observatories serve not only to illuminate the unknown, but also to connect humanity with the cosmic mechanisms that shape our existence. The Oort Cloud stands as a testament to the enduring quest for discovery at the fringes of our solar neighborhood. The connection between the Oort Cloud and solar system evolution reveals intricate processes that shaped this celestial neighborhood. This distant region is believed to contain countless icy bodies, remnants from the formation of the solar system over 4.5 billion years ago. These ancient materials offer insights into the primordial conditions that prevailed during the early stages of planetary development. Composed primarily of water ice, ammonia, and methane, these objects serve as a record of the solar system's evolution. Their orbits, elongated and highly eccentric, provide clues about the gravitational interactions that have occurred over millennia. As they drift through the vastness, some of these bodies may be nudged into the inner solar system, becoming long-period comets that illuminate our night sky. The study of these comets enhances understanding of the processes that led to the formation of the terrestrial planets. They may have delivered essential organic compounds and water, crucial components for the emergence of life. Understanding the Oort Cloud's dynamics also informs the theories surrounding the solar system's stability and long-term evolution. Observations of this region, though challenging due to its vast distance, continue to evolve with advancements in technology. As researchers refine their techniques, the knowledge gleaned from the Oort Cloud will undoubtedly deepen the comprehension of our cosmic neighborhood. The dynamics of the Oort Cloud present a myriad of challenges for scientists seeking to unlock its mysteries. Vast distances obscure direct observation, leaving the understanding of its structure and composition reliant on indirect measurements. This region, believed to be a vast reservoir of icy bodies, raises questions about its formation and evolution. Theoretical models suggest that gravitational interactions with nearby stars and galactic tides play critical roles in shaping its dynamics, yet precise mechanisms remain elusive. Current research gaps highlight the need for improved simulations that incorporate the complexities of these interactions. Observations of long-period comets, which are thought to originate from this distant reservoir, offer tantalizing clues yet lack the granularity required for definitive conclusions. The distribution of these icy bodies hints at a more intricate formation history than previously thought, suggesting a dynamic interplay among various forces over billions of years. Understanding the Oort Cloud's boundaries also poses a significant challenge. The exact extent of this distant region, often described as a spherical shell surrounding the solar system, remains uncertain. Defining these limits is essential for constructing accurate models of solar system evolution. Continued exploration and technological advancements promise to illuminate these gaps, gradually revealing the hidden behaviors and characteristics of this enigmatic frontier. The structure of the Milky Way exerts a profound influence on the Oort Cloud, shaping its formation and the dynamics of its constituents. This colossal spiral galaxy, with its dense core and sprawling arms, generates gravitational forces that extend into the far reaches of the solar system. These forces can perturb the orbits of icy bodies within the Oort Cloud, occasionally sending them on trajectories that bring them closer to the inner solar system. Interactions with neighboring stars also play a significant role. As stars move through the galaxy, their gravitational interactions can disturb the delicate balance of objects within this icy shell. Such encounters can result in the ejection of some bodies into interstellar space, while others may be nudged into the inner solar system, where they become visible as comets. The position of the solar system within the Milky Way further complicates the dynamics at play. Located in one of the spiral arms, it is subject to varying gravitational influences depending on its orbit around the galactic center. The distance from this center also affects the density of nearby stars, impacting the likelihood of close encounters over astronomical timescales. Understanding these intricate interactions provides essential insights into the behavior and evolution of this distant region, deepening comprehension of the solar system's broader context within our galaxy. The vastness of the Oort Cloud offers a unique perspective when compared to other stellar systems. Each system possesses its own distinct characteristics, often shaped by the gravitational influences of nearby stars and the surrounding interstellar medium. In contrast, this distant region is predominantly isolated, resulting in a unique collection of icy bodies and comets that reflect the solar system's formation history. Investigations into other stellar systems reveal variations in cloud structures, with some exhibiting dense rings of material, while others possess sparse distributions of debris. These differing configurations provide clues about the formative processes that led to their current states. Comparisons with the Oort Cloud highlight the effects of local gravitational interactions on the retention and arrangement of icy bodies. Observations of exoplanetary systems suggest that many may lack a comparable outer shell, possibly due to different evolutionary paths or dynamic encounters with other celestial objects. The presence or absence of such structures can significantly influence the development of planetary atmospheres and the potential for habitability. Continued exploration of these systems enhances understanding of not only their individual characteristics, but also the universal principles governing the formation and evolution of planetary systems, including our own. Each discovery adds another layer to the intricate puzzle of cosmic evolution, illuminating the shared destiny of celestial bodies across the universe. Theoretical impacts of nearby supernovae on the Oort Cloud suggest significant perturbations within this distant region. When a massive star reaches the end of its life cycle, it can explode with tremendous force. The shock waves generated by such events have the potential to disturb the delicate equilibrium of icy bodies located at the cloud's boundary. These shockwaves can create gravitational disturbances, nudging comets and other objects toward the inner solar system. In this context, the Oort cloud acts as a reservoir of ancient material, remnants from the formation of the solar system. The interaction between shockwaves and these icy bodies is thought to be a driving force for the occasional influx of comets into the inner solar system. It is estimated that a supernova occurring within a distance of approximately 30 light-years could have a profound effect, possibly triggering a cascade of cometary activity. The implications of such events extend beyond mere cometary paths. Alterations to the Oort cloud could also influence the dynamics of the entire solar system. The gravitational interactions might lead to the ejection of some objects into interstellar space while drawing others closer to the Sun, creating a complex interplay of forces that shapes both the past and future trajectories of these celestial bodies. Understanding these phenomena reveals the intricate connections between stellar life cycles and the evolution of our solar neighborhood. The Oort cloud serves as a vast laboratory for gravitational physics, situated at the boundary of our solar system. This region, comprised of icy bodies and primordial material, is believed to extend from approximately 2,000 to 100,000 astronomical units from the Sun. Within this expanse, the gravitational influence of nearby stars and the galactic center plays a critical role in shaping the dynamics of celestial objects. Interactions among these objects create a complex gravitational landscape. Perturbations from passing stars can send comets towards the inner solar system, providing insights into their origins and the physics governing their trajectories. Each encounter offers a unique opportunity to study gravitational interactions on a grand scale, where the subtle forces at play can alter the course of entire icy bodies. Observations of this distant region also contribute to our understanding of dark matter and its effects on gravitational fields. Fluctuations in the distribution of mass can be monitored through the movement of these comets, helping to refine models of gravitational interactions in both our solar system and beyond. The Oort cloud, with its ancient remnants, stands not only as a relic of the solar system's formation but also as a crucial space for investigating the fundamental principles that govern celestial mechanics, revealing the delicate interplay between gravity and motion in a universe still unfolding. Satellites play a pivotal role in the exploration and understanding of this distant region. Equipped with advanced sensors, they gather data that can penetrate the vast distances between Earth and the Oort cloud. These instruments measure light spectra, tracking the chemical composition of cometary bodies that occasionally venture into the inner solar system. Each encounter provides insights into the primordial materials that formed the solar system. The vast expanse of the Oort cloud, estimated to extend from approximately 2,000 to 100,000 astronomical units from the Sun, presents substantial observational challenges. Ground-based telescopes, hindered by atmospheric interference, are limited in their ability to capture the faint signals emitted by these distant objects. Satellites, positioned beyond the atmospheric veil, offer a clearer view of the sky, allowing for the collection of data that is both precise and expansive. Through careful analysis, these observations contribute to our understanding of the dynamics of icy bodies. Notably, they help to illustrate the gravitational influences that govern their orbits. This ongoing research illuminates the history of our solar system, as well as the complex interactions that may have implications for understanding planetary formation processes throughout the cosmos. The data captured by these satellites continues to reshape our comprehension of the universe's distant reaches. The significance of public outreach in Oort cloud research cannot be overstated. Engaging the public fosters a collective understanding of the complexities surrounding this distant region. Educational programs and community events serve to bridge the gap between scientific inquiry and societal awareness. They illuminate the implications of findings related to the Oort Cloud, demonstrating how these icy bodies contribute to our understanding of solar system formation and evolution. This region, often shrouded in mystery, benefits from the curiosity and enthusiasm of interested individuals. When scientists share their discoveries, they spark interest and inspire the next generation of researchers. Public lectures, online forums, and interactive exhibits provide venues for dialogue, allowing diverse perspectives to enrich the scientific narrative. Collaboration with educational institutions enhances outreach efforts. Schools can incorporate Oort Cloud studies into their curricula, presenting complex concepts in an accessible manner. This approach not only cultivates interest in astrophysics, but also emphasizes the relevance of space science to everyday life. As the exploration of the Oort Cloud progresses, maintaining public engagement becomes crucial. It ensures that knowledge is disseminated widely, promoting informed discussions about the importance of space exploration. Such initiatives underscore the interconnectedness of humanity and the cosmos, highlighting our collective quest for understanding the universe that surrounds us. The ethical considerations surrounding space exploration of the Oort Cloud raise complex questions about humanity's role in the cosmos. This distant region, filled with icy bodies and potential resources, invites both curiosity and caution. The prospect of mining resources from these ancient remnants of the solar system poses dilemmas regarding ownership and stewardship. The vast emptiness of the Oort Cloud does not negate the responsibility to preserve its integrity. Interactions with these primordial materials could hold implications for planetary protection. Contamination of celestial bodies, even those far removed from Earth, poses risks to the pristine environments that may harbor unknown forms of life. Exploring the Oort Cloud necessitates a commitment to safeguarding these untouched realms, ensuring that exploration does not lead to irrevocable harm. The potential for scientific advancement must be weighed against the moral implications of exploitation. This region serves as a time capsule of the solar system's formation, offering insights into our origins. Respecting this legacy can guide ethical frameworks surrounding exploration missions. Collaborative international efforts are essential in establishing regulations that govern activities in the Oort Cloud. Such agreements foster a sense of unity among nations, guiding humanity toward a sustainable and respectful approach to the cosmos. The balance between exploration and preservation remains a pivotal aspect of future endeavors in this distant frontier. The potential for discovering new physics in this distant region instills a sense of curiosity among scientists. Observations of the Oort Cloud may reveal insights into the formation of our solar system, offering clues to the processes that governed its evolution. This icy expanse is thought to contain ancient remnants from the primordial solar nebula, preserved in a state of stasis. Such materials may provide a unique opportunity to study matter that has not undergone significant alteration over billions of years. Investigations into the dynamics of these distant objects could uncover novel gravitational interactions, challenging existing models of celestial mechanics. The interactions between comets and trans-Neptunian objects may yield evidence of phenomena that remain largely theoretical in current astrophysical frameworks. Each fragment within this region serves as a time capsule, potentially holding secrets that could reshape our understanding of cosmic history. The presence of exotic materials, possibly including organic compounds or even unknown forms of ice, may also prompt re-evaluations of chemical processes in the early solar system. Researchers anticipate that future missions to the Oort Cloud will not only expand knowledge of our own planetary neighborhood, but may also illuminate the fundamental laws governing the universe. Each discovery contributes to a broader narrative, revealing the interconnectedness of celestial bodies and the mechanisms that orchestrate their existence. The magnetosphere serves as a protective barrier for Earth, generated by the planet's magnetic field. This region effectively shields the atmosphere and surface from the solar wind and cosmic radiation. The Oort Cloud, situated at the fringes of the solar system, plays a subtle yet significant role in this dynamic. Comets originating from this distant reservoir can affect Earth's magnetosphere upon their approach. As these icy bodies venture inward, they interact with solar wind, generating ionization that can have localized effects on the magnetic field. The presence of these comets contributes to the complexity of space weather. When they approach the inner solar system, the solar wind's interaction with the cometary material can enhance or disrupt the magnetosphere's stability. This interaction may lead to variations in geomagnetic activity, which are monitored closely by scientists. Fluctuations in the magnetosphere influence not only electromagnetic phenomena, such as auroras, but also satellite operations and communication systems. Shifts in this delicate balance necessitate ongoing observation. Understanding the relationship between the Oort Cloud and Earth's magnetosphere informs predictions regarding space weather. It underscores the intricate ties binding distant regions of the solar system to terrestrial conditions, revealing the profound interconnectedness within our cosmic neighborhood. Each comet's journey becomes a reminder of the complex forces at play in shaping planetary environments. Advanced algorithms play a crucial role in interpreting the vast and intricate data gathered from the Oort Cloud. The sheer volume of information, encompassing positions, velocities, and compositions of countless icy bodies, requires sophisticated computational strategies to discern meaningful patterns. These algorithms are designed to sift through noise, identifying potential comets and their trajectories with precision. Machine learning techniques enhance predictive models, allowing scientists to anticipate future comet paths and interactions. By training on historical data, these systems improve their accuracy, revealing previously hidden relationships between celestial objects. Such insights contribute to a deeper understanding of the origins and dynamics of the Oort Cloud itself. Data visualization techniques further enhance comprehension, transforming raw numerical data into accessible graphical representations. These visualizations help convey the distribution of objects within the cloud, illustrating how gravitational influences affect their orbits. They also facilitate the identification of clusters and gaps, shedding light on the formation processes that led to this distant region. As researchers refine their algorithms, they unlock new avenues of inquiry, enabling more detailed investigations into the cloud's structure. This ongoing analysis fosters collaboration across disciplines, bridging astrophysics with computer science. The interplay of advanced algorithms and Oort Cloud data. The interdisciplinary nature of Oort Cloud studies reveals the intricate connections between various fields of science. Astrophysics provides the foundational understanding of celestial mechanics, enabling researchers to model the dynamics of icy bodies within this distant region. Mathematics becomes essential, employing complex equations to predict the orbits of comets and the gravitational influences exerted by nearby stars. Planetary science contributes insights into the formation and evolution of the solar system, offering explanations for the distribution of materials found in the Oort Cloud. These frozen remnants of planetary formation hold clues to the early conditions that shaped terrestrial and gas giant planets. Astronomy plays a critical role, utilizing telescopes and observational techniques to identify and track these elusive objects. As light from the sun diminishes in this vast expanse, specialized instruments and methodologies are required to detect and analyze the faint signals emitted by Oort Cloud entities. The integration of these disciplines fosters a comprehensive understanding of the Oort Cloud's structure and composition. This region serves as a cosmic time capsule, preserving the remnants of the solar system's formative years. Each icy body carries with it a history, offering a glimpse into the processes that govern planetary systems. In this way, the study of the Oort Cloud enriches multiple scientific narratives, bridging gaps between fields and illuminating the complexities of our celestial neighborhood. Solar activity exerts a profound influence on the dynamics of Oort Cloud objects. This region, situated at the periphery of the solar system, is populated by countless icy bodies, remnants from the early solar nebula. The energy emitted by the sun, in the form of solar wind and radiation, interacts with these distant entities, subtly altering their trajectories over time. Periodic solar storms generate fluctuations in the solar wind, which can disturb the orbits of these objects. The effects, while gradual, accumulate, leading to potential perturbations in their paths. The gravitational pull of the sun, combined with the influence of nearby stars, contributes to the distribution and movement of these icy bodies, some of which may be nudged into the inner solar system. This interaction extends beyond mere displacements. Solar radiation can induce physical changes on the surfaces of these objects, causing sublimation of volatile materials and altering their reflective properties. As these icy bodies travel through the solar system, they may become active comets, displaying tails that reflect their shifting states. Understanding these processes sheds light on the broader implications for planetary formation and the evolution of the solar system. Each object within this vast expanse serves as a record of the conditions present in the early solar system, revealing the intricate dance between solar activity and the cosmic remnants that linger at the edge of this celestial realm. The potential for astrobiological discoveries within the Oort Cloud is an area of growing interest. These icy bodies, composed primarily of frozen gases and organic materials, may harbor the building blocks of life, preserved in their frigid interiors. The extreme cold of this environment acts as a natural preservative, maintaining the original chemistry that might have existed during the solar system's formation. Analysis of these objects could yield insights into prebiotic chemistry, offering clues about how life might arise in similar conditions elsewhere in the universe. Comets, often considered the most accessible representatives of the Oort Cloud, have been shown to contain complex organic molecules, including amino acids and other essential components for life. The study of these bodies may also inform our understanding of how life could survive under extreme conditions. In particular, the potential for microbial life to exist in subsurface oceans has been a topic of scientific inquiry, drawing parallels with environments on icy moons in our own solar system. Exploration missions targeting these distant remnants may not only enhance knowledge about the origins of life on Earth, but also extend the search for extraterrestrial life. Such endeavors could enhance understanding of the formation and evolution of the solar system. The Oort Cloud serves as a reservoir of primordial material, offering insights into the conditions present during its early development. Examination of the icy bodies within this distant region reveals data that can inform theories regarding planet formation, as well as the dynamics of gravitational interactions in the outer solar system. The study of these frozen remnants has implications that extend beyond mere historical context. They may harbor organic compounds and other elements essential for life, prompting questions about the potential for life's origins beyond Earth. It fosters a deeper comprehension of the chemical processes that occurred in the early solar system, contributing to the broader field of astrobiology. Observation of the Oort Cloud also sheds light on the mechanical processes that govern comets, their trajectories, and their potential impact on terrestrial environments. The long-period comets originating from this region can serve as time capsules, carrying clues about the solar system's infancy. This unique area, often overlooked, requires innovative methods for exploration, inspiring advancements in technology and scientific instruments. Each discovery adds layers to our understanding of celestial phenomena, reinforcing the interconnectedness of cosmic events and the ongoing quest for knowledge in astrophysics. Thus, research in the Oort Cloud continues to enrich both scientific discourse and educational endeavors. The enigmatic nature of the Oort Cloud extends beyond its icy inhabitants, drawing intriguing connections to dark energy. This region, largely unexplored, holds clues that may enhance understanding of cosmic evolution and the universe's expansion. Theoretical models suggest that as the Oort Cloud interacts with other celestial bodies, it may influence gravitational dynamics, revealing insights into the behavior of dark energy. These icy bodies, remnants from the solar system's formation, are believed to contain primordial materials that can provide data on the early universe. Their composition, largely untouched for billions of years, could reflect the conditions under which dark energy began to dominate cosmic expansion. Studies of these objects enhance the understanding of how dark energy influences galactic formation and distribution. Observations of the Oort Cloud may also serve as a window into the cosmic web, the structure of the universe that emerges from the interplay of gravity and dark energy. By analyzing the orbits and trajectories of these distant objects, researchers can infer the gravitational influences at play, offering a clearer picture of the elusive force driving the universe's accelerated expansion. This quiet frontier encapsulates the ongoing quest for knowledge, bridging the gap between the tangible remnants of the solar system and the abstract concepts of dark energy. The future of theoretical models concerning this region hinges on advancements in observational technology and computational methods. Enhanced telescopes equipped with advanced imaging capabilities will allow for more detailed surveys of the Oort Cloud, potentially revealing new objects and their properties. These observations will refine existing models, providing deeper insights into the cloud's structure and composition. Simulations play a crucial role in understanding the dynamic processes that govern the formation and evolution of these icy bodies. By integrating data from direct observations with theoretical frameworks, researchers can create more accurate representations of how the Oort Cloud interacts with the solar system. This includes the influence of stellar encounters and galactic tides, which may periodically disturb the cloud, sending comets toward the inner solar system. As these models evolve, they will contribute to a broader understanding of solar system dynamics and the history of planetary formation. The implications extend beyond our immediate neighborhood. Observations of similar structures around other stars could provide comparative data, illuminating the universality of such phenomena in different stellar environments. In this context, the Oort Cloud serves not only as a repository of ancient solar system material, but also as a vital key to unlocking fundamental questions about the nature of matter and energy in the cosmos. Each discovery brings humanity closer to a cohesive understanding of its place in the universe. And the person Horster of Lostran Sossos, a vast spherical shell of icy bodies, marking the outermost boundary of the solar system. It is believed to contain trillions of comets, remnants from the early solar system's formation. This region plays a critical role in the evolution of life on Earth, acting as a reservoir of these primordial materials. Occasionally, gravitational perturbations can send comets hurtling toward the inner solar system, where they may intersect with terrestrial planets. These icy bodies are rich in organic compounds and water, essential ingredients for the emergence of life. Impacts from these comets have likely contributed to Earth's oceans and atmosphere, creating environments conducive to biological development. The delivery of such materials would have provided the necessary components for prebiotic chemistry, facilitating the transition from simple molecules to complex organic structures. The Oort Cloud also influences the long-term stability of the solar system. By absorbing rogue objects and redirecting potential impactors, it serves as a protective barrier. Its existence underscores the interconnectedness of celestial mechanics and biological evolution on Earth. The ongoing study of this distant region continues to yield insights into the processes that shaped our planet and the conditions necessary for life to thrive. Understanding the Oort Cloud enhances our grasp of cosmic evolution and the delicate balance that sustains life. Collaboration among scientists is vital for advancing knowledge of the Oort Cloud. Experts from various fields unite to analyze data from space probes, telescopes, and theoretical models. This region, located approximately 1,000 to 100,000 astronomical units from the Sun, presents challenges that require diverse expertise. Astronomers, physicists, and planetary scientists work together to piece together the cloud's elusive structure and origins. Observations made by missions, such as those from the Voyage spacecraft, provide essential insights into the composition and behavior of long-period comets that may originate from this distant area. Ground-based observatories contribute complementary data, enhancing the understanding of the cloud's dynamics. Advanced computer simulations allow researchers to visualize how gravitational interactions and stellar encounters might influence its formation and evolution over time. International partnerships amplify these efforts, facilitating the sharing of resources and findings. Conferences bring together minds from around the globe, fostering discussions that ignite new ideas and collaborative projects. Ongoing studies continue to refine models, revealing the cloud's intricate relationship with the solar system's history. Through this concerted effort, the scientific community strives to unravel the mysteries surrounding this icy reservoir. This icy reservoir holds the potential to be a significant resource for future space exploration. Composed primarily of icy bodies, it is hypothesized that these materials could serve as vital sources of water, essential for sustaining human life during prolonged missions beyond Earth's atmosphere. The presence of volatile compounds within these remnants of the solar system's formation may also provide necessary fuel for propulsion systems, reducing the need to transport all supplies from Earth. In this distant region, the abundance of comets offers insights into the primordial conditions that shaped the solar system. They contain unaltered material that has remained relatively unchanged for billions of years, presenting opportunities to study the building blocks of planets and the origins of organic compounds. Such findings could enhance our understanding of life's potential elsewhere in the universe. As technology advances, missions could be designed to venture into this cloud, utilizing robotic explorers to harvest these resources. This endeavor would require careful planning and innovation, as the vast distances involved and the challenging environment present considerable obstacles. Yet, the possibility of utilizing the Oort Cloud as a stepping stone for deeper space exploration remains an intriguing prospect. It may transform humanity's approach to interstellar travel, ensuring that the exploration of the cosmos is sustainable and self-sufficient. The age of this region remains a complex enigma, presenting substantial challenges to scientists. Estimations regarding its formation hinge on understanding the early solar system's dynamics, which are intricately tied to the gravitational influences of nearby stars and the solar nebula's collapse. These factors contribute to the uncertainty surrounding the exact timeline of the Oort Cloud's emergence. Models suggest that it may have developed over billions of years, possibly forming shortly after the gas giants settled into their current orbits. The delicate balance between solar winds, radiation, and gravitational forces plays a crucial role in shaping its structure. Direct observation is hindered by its vast distance and the faintness of its icy bodies. Consequently, researchers rely on indirect methods, such as studying comets and their trajectories, to infer the cloud's characteristics and age. The interaction between the Oort cloud and external forces, such as passing stars, further complicates this understanding. These encounters can perturb objects within the cloud, ejecting them into the inner solar system as comets. The remnants of these interactions provide key insights into the cloud's history. Clarity in this domain illuminates not just the Oort cloud's past, but also the broader narrative of solar system evolution. Each discovery adds a piece to the complex puzzle of our cosmic surroundings, gradually refining humanity's comprehension of its origins. International space agencies play a pivotal role in advancing research related to the Oort cloud, an enigmatic region that lies at the fringes of the solar system. Collaborative efforts among these organizations facilitate a deeper understanding of its structure and formation. Missions designed to explore the outer solar system often include instruments capable of detecting the faint signals emanating from this distant area. Data collection from satellite observations contributes significantly to mapping the Oort cloud's boundaries and density. These observations allow scientists to analyze the distribution of icy bodies and their potential interactions with incoming cosmic phenomena. The coordination among different countries enhances the pooling of resources and expertise, fostering innovative methodologies to study this remote environment. The development of advanced telescopes, both ground-based and orbital, enables researchers to gather crucial information regarding the composition of Oort cloud objects. Through spectroscopic analysis, the chemical signatures of these distant bodies reveal their evolutionary history and shed light on the conditions present during the solar system's formation. Joint missions, such as those involving elements of planetary science and astrophysics, ensure that findings are shared across borders. Collaborative research initiatives leverage the diverse strengths of various agencies. The legacy of the Oort cloud extends far beyond its icy constituents. Understanding this distant region is essential for piecing together the history of our solar system. Theoretical models suggest that the cloud is a remnant from the formation of the solar system, holding clues to the processes that shaped the inner planets. Analyzing the composition and distribution of these icy bodies provides insights into the primordial materials that contributed to planetary formation. Examining the Oort cloud may also reveal the nature of long-period comets, those celestial wanderers that originate from its depths. Tracking their trajectories can enhance knowledge of gravitational influences exerted by nearby stars and the galactic environment. This interaction is critical for comprehending how these objects evolve and how they may at times approach the inner solar system. Observations of this region could further elucidate the conditions that prevail in the outer solar system, including temperature variations, density, and the impact of solar radiation. Such data will refine existing models and may lead to the discovery of previously unrecognized phenomena. The quest to understand the Oort cloud is not merely academic, it holds the potential to inform future missions and enhance preparedness for any celestial events that may arise from these icy realms. Advancements in technology are paving the way for more detailed observations of this region. Next-generation telescopes, equipped with enhanced sensitivity and resolution, will allow astronomers to peer deeper into the Oort cloud's structure. Observations across various wavelengths will unveil the composition of these icy bodies, revealing the chemical processes that govern their formation. Collaborative efforts among international space agencies aim to implement missions specifically targeting this vast expanse. Proposed spacecraft will traverse beyond the known boundaries of the solar system, venturing into the Oort Cloud to gather direct measurements. Such endeavors may yield invaluable data on the primordial materials that contributed to the formation of planets. Research is also focusing on the dynamics of objects within this distant sphere. Understanding the gravitational influences exerted by nearby stars and the galactic environment will shed light on the stability and evolution of these distant icy bodies. This insight will be crucial for predicting potential encounters with the inner solar system. The theme implications extend beyond mere exploration. The study of the Oort Cloud offers clues to the origins of water and organic molecules on Earth, further connecting cosmic processes to planetary development. Each revelation in this icy frontier unfolds a deeper narrative about the vast cosmos and humanity's place within it. The role of citizen science emerges as a pivotal component in unraveling the mysteries of this remote region. Enthusiastic amateurs contribute to significant discoveries, often utilizing advanced observational techniques and tools that were once reserved for professional astronomers. Collaborative platforms enable individuals to analyze vast amounts of data, allowing for the identification of potential comets and other celestial bodies that drift from the Oort Cloud. This engagement fosters a sense of community among those passionate about astronomy, bridging the gap between professional and amateur realms. Through collective efforts, these observers enhance the understanding of not only the Oort Cloud, but also the dynamics of the solar system as a whole. Each observation, meticulously documented and shared, becomes a vital piece of the larger puzzle, illustrating how diverse perspectives enrich scientific inquiry. The contributions of citizen scientists also extend to the refinement of existing models of solar system formation. Insights gained from these volunteers can challenge established theories, prompting further investigation into the origins and evolution of the Oort Cloud. This symbiotic relationship between seasoned researchers and eager amateurs exemplifies the evolving nature of scientific exploration, demonstrating that the quest for knowledge is a shared endeavor, transcending traditional boundaries and inviting all to participate in the quest to unveil the cosmos. The philosophical implications of studying the Oort Cloud extend beyond mere scientific inquiry. This distant region, shrouded in ice and mystery, invites contemplation about humanity's place in the universe. It serves as a reminder of the vastness that surrounds Earth, challenging the perception of our planet as the center of existence. The knowledge gleaned from this exploration fosters a sense of humility, revealing the limits of human understanding while simultaneously igniting curiosity. Encounters with the Oort Cloud raise questions about the origins of the solar system and the processes that govern celestial bodies. Observations suggest that these icy objects may hold remnants of the primordial materials that formed the planets. Such insights provoke reflection on the nature of existence, prompting inquiries into the beginnings of life itself and the conditions necessary for its emergence. The study of this region also urges a reconsideration of timescales. The Oort Cloud, with its estimated formation over 4 billion years ago, presents a perspective that dwarfs human history. It emphasizes the transient nature of civilizations in the face of an enduring cosmos, urging a deeper appreciation for both the fleeting and the eternal. In contemplating these elements, the pursuit of knowledge becomes a conduit for philosophical exploration, connecting humanity to the broader narrative of the universe. This connection inspires both wonder and responsibility in preserving the delicate balance of the cosmic environment. The Oort Cloud represents a frontier of cosmic exploration, a vast and largely uncharted region that envelops the solar system. It is a realm characterized by icy bodies, remnants from the formation of the solar system, existing in a state of frozen isolation. These distant objects, often considered the building blocks of comets, hold secrets about the early solar system and the processes that shaped it. Exploration of this region poses significant challenges, given its immense distance and the faint signals emanating from its inhabitants. Robotic spacecraft traversing the void may one day reveal insights hidden within the icy shells that drift silently through space. The composition and distribution of these celestial entities could provide vital information about the origins of water on Earth and the potential for life elsewhere. This outermost zone also plays a crucial role in understanding the dynamics of our solar system. Perturbations caused by nearby stars and the galactic environment can send objects from the Oort Cloud spiraling inward, potentially impacting inner planets. This delicate equilibrium highlights the importance of studying these far-off remnants, as their trajectories could influence planetary environments in unforeseen ways. The Oort Cloud stands as a testament to the complexity of our celestial neighborhood, inviting continued inquiry into the nature of the cosmos and our place within it.